Hi, I'm Jerry Huang from Rensselaer Polytechnic Institute. In today's video, I am representing my co-author Samuel Chabot and my advisor Jonas Brasch to present our work on Panoptic Reconstruction of Immersive Virtual Soundscapes using human-scale panoramic imagery with visual recognition. First, some background and goals for this work. The project is situated at Rensselaer's collaborative research Augmented Immersive Virtual Environment Laboratory, short for CRAIVELab. It is a room-centered immersive virtual reality system for human-scale audiovisual display research that consists of a panoramic display and 128-channel waveview synthesis loudspeaker array. The CRAIVELab has a track record of research specifically dedicated to spatially and perceptually congruent audiovisual co-representation. The work ranges from using ambisonic field recording for soundscape mapping to using machine learning methods for audio classification and real-time rendering. One common feature of these works is the co-collection of spatially accurate audio and visual data. While such data collection technique does seem to produce reliable audiovisual representation in the virtual reality system like the CRAIVELab, it does not reflect real-world scenario where the efficiency of spatial capture does not match in between visual and audio elements. More often, one will be able to take panoramic images more ubiquitously than recording high-fidelity spatial audio, which makes us speculate the possibility of reconstructing the acoustic environment based upon structured visual data. This is where the significance of this work comes in. It serves as a proof of concept that construct plausible and congruent virtual soundscapes that are based solely upon visual information provided by captured physical environments. In this effort, we would like to examine its efficiency and effectiveness of the soundscape to convey the same contextual information that the panoramic imagery presents. Now I would like to talk about our methods. We draw reference to existing standardization framework of soundscape per ISO 12913, which is influenced by R. Murray Schafer's taxonomic framework. In the taxonomy, he defines three elements: keynote, signal, and soundmark. In ISO standards, these have been translated to foreground, background, and environmental context. We found analogs in the visual domain, and we are interested in using two visual recognition algorithms. Semantic segmentation classifies image regions into meaningful visual elements on a pixel-by-pixel basis, which we consider helpful to facilitate the rendering of background sound. Object detection extracts spatial information within images for quantifiable visual entities, which we use for assembling foreground sound elements. For datasets, we use handcrafted panoramic images that are adjusted for display at the CRAIVELab as visual ground truth. We use two existing image datasets for two pre-trained visual recognition models, which collectively represent 100 visual element classes. We designate 32 of them as sound element classes and correspond them with synthetic and recorded audio datasets. The soundscape generation process goes as follows. After the assembly of panoramic images from their corresponding HDR image snippets, we subdivide them into equally dimensioned segments in adjustment to the resolution of pre-trained visual recognition models. We use ENet for semantic segmentation and YOLO v3 for object detection, and process the segments one by one before assembling them together. For the recognized results, we can extract spatial and symbolic information from sound objects, including their quantities, what they represent, and where they are in terms of angular positions. We then use a method similar to a pinhole camera model to approximate the object's radial distances and adjust them for calibration gains. For foreground sounds, we address the mapping by directly representing them as virtual sound sources. For background sounds, we use a region-based approach, which determines the center of gravity for ambient sounds relative to the loudspeaker distribution, and introduce a spread that is associated with the span of the region. We adopt a simultaneous onset for each sound object class but vary the onset time for individual instances of the same class. So how does it perform? We designed and developed the system using Python that connects with Max MSP. And this is the mapping result for one panoramic image in Max MSP using RCam SPAT. As one can observe, the results indicates that the rendering scheme constructed through visual recognition is capable of generating sound objects from detected visual objects. And the population and density of sound objects suggests that the granularity of soundscape could be achieved with coherent perceptual tuning. For optimizing efficiency, we test the design system against different subdivision schemes for panoramic images without losing their information and without compromising the performance of the pre-trained visual recognition model we use. We have found that the number of sound objects detected is dependent on the segmentation of panoramic images. Increasing subdivision does not ensure the increment of sensitivity for sound object extraction, but visual recognition models are effective for the purpose of sound object generation across all of these schemes. One question that arises is, what kind of sound objects are there in the soundscape? This is the graph about the average number of sound object instances for each class across all panoramic images examined. As could be observed, persons are detected most, followed by vehicles and animals. This is aligned with the general setting of the panoramic image dataset, which contain primarily outdoor settings with urban context. So, this work presented here suggests several future research directions that could be taken. For example, the performance of the designed soundscape reconstruction system could be optimized using more robust visual recognition models with data parallelism for real-time processing. The system could be further improved by incorporating a reverberation database to accommodate enhanced simulation quality for indoor spaces, as well as geographically oriented data for generating culturally oriented sound with site-specific knowledge. In addition, a blind testing could be conducted by engaging the immersants at the CRAIVELab with only the reconstructed soundscapes and compare their perceived context with visual ground truth to determine the degree of congruence and the adequacy of soundscape representation given by the system. Thank you for your time, and that's the end of the presentation.
Another really interesting project, and this one I'm pleased to see that you are very interestingly basing on Schaefer's ontology of soundscape elements. Just in case people are writing questions right now, but there aren't any currently, I'm going to ask one question. Have you looked into the way that game sound engines, like particularly adaptive interactive frameworks for game sound engines work? Because it's very, very similar in a way to what you're describing in terms of populating a kind of virtual sound environment.
Correct. I think we are particularly interested in using the similar game sound engine model for a room-centered immersive systems like CRAIVE. I think we're focusing primarily on, instead of focusing on individual experiences, we focus on the situation when a lot of people are presented in the room and want to share the experience together. The game engine aspect of this kind of research is kind of nascent in our group. So but we do have a lot of panoramic images present, and we have a system that is being designed and implemented at CRAIVE that can allow for basically instant drag and drop scenario of geographically based panoramic image display based upon map information. So I think our next step for designing this kind of system is to sort of incorporate the soundscape elements using those geographically based images. But to answer your question a little bit more specifically, I think the model that we're trying to adopt is similar to the ones that exist in game engines, but we are not using the three-dimensionality of game engine because we only have the visual information of two-dimensional images to rely on. So we kind of, in this case, we kind of predict the three.
Yeah, you approximate. Yeah. Great work. Really, really interesting. I'd be curious to keep up with it. There is a question in the Q&A now, and that would be, unfortunately, the last question because we're running slightly over time. Have you compared your soundscapes to recordings with multi-channel microphones? What are the advantages or disadvantages?
We do not have the ground truth of multi-channel microphone recordings for the same environment that we captured visually. So the only reference point that we have is basically the visual information present. But we do have situations when there are higher order ambient audio being captured for audio classification purposes, as I mentioned in President's research, they are being segmented for analysis. And we have yet to capture the images associated with those audio yet, but that's kind of in our plan. So once we have the visual data for those environments, we'll be able to run a comparison between the ambisonic field recording and the generated soundscape. There's also the hypothesis that you cannot completely derive the complete acoustic environment just based upon visual information, because so much of those information are not,
of course,
present. So we have to use additional machine learning model to determine the context of those environments in order to further enrich the sound that is already generated.